transforms and frequency response functions. So we have talked about each of these individually, and we're going to try to bring them together now in this lecture. And then I'm going to talk somewhat about Laplace transforms on Friday, and then we're going to be done with system dynamics. I know, right? And then we're going to do some controls. It's going to be awesome.
Do we need to get another book for that?
It's the Nice textbook. You can get an old version. I don't care. Like, the older editions are totally fine to use. The homework will be out of the latest edition, but just know somebody with the latest edition, and then you're good. I mean, it hasn't changed much. Yeah.
Did you order it at the school store? Bookstore?
I think so, yeah. Sounds familiar. Pretty sure I did. Yeah. So, the Nice textbook is it's a great book, and if you end up doing more controls with me, like in another class later on, like a robotics and automation, it's offered next year, that type of thing, we use it again. Actually, I don't know. We'll see. So we're supposed to. My schedule got shook up this next year, so it was shaken up. I like shook up better. That sounds cooler. So, Fourier transforms and frequency response functions. So Fourier transforms, which we talked about last lecture, can be used to characterize the steady state response of a system to a sinusoidal input, and also to many other types of inputs. So we're going to focus today on a sinusoidal input, but we're in general interested in any type of input. So let U of t be the sinusoidal input, Y of t be the output, and A and B be constants. A single input, single output system has this representation. And I think this is all filled in for you, right? Yeah. I think so we have these time derivatives of the output on the left-hand side, and we have these time derivatives of the input on the right-hand side of the equation. Very familiar at this point. We can take the Fourier transform of each side, which we just learned how to do, the Fourier transform, but we're just going to start applying it, and in a very color-coded way, we will march through these equations. The first line says, okay, I'm going to take the Fourier transform of the left-hand side of the equation. On the right-hand side, I'm going to take the Fourier transform as well. And we learned last time that if you take the Fourier transform of A plus B, you can take the Fourier transform of A and add it to the Fourier transform of B. Remember that? We did talk about it. So that's what we did in this first step. We said, okay, if you're going to take the Fourier transform of a sum, we can take the sum of the Fourier transform. So easy enough, we just distributed it. Also, we said that if you have a scalar multiplication of a function, then it just is a scalar multiplication of the Fourier transform as well. So you can think of it as pulling the constant outside. The Fourier transform is an integral, right? That was the definition. And so the properties of integration apply here, where if you have something that's scaled inside the integral, then you can pull it outside the integral, the scaling factor outside the integral, right? If you were to integrate 5x squared, you could pull the 5 out of the integral, right? That's essentially what we did in this step as well. So we did that. And then there was this property of what happens if you have a derivative, a time derivative, and you want to know, so say you have the time derivative of y right here. You want to know what the Fourier transform is of that. We learned it's j omega times the Fourier transform of y. right? So the derivative has the effect of just being a multiply of j omega. And if you have the second time derivative or the third time derivative, we just have a j omega multiplied by however many derivatives there are. So j omega raised to however many derivatives that term has, we have show up. This is very similar to something that we did before with the s's. Remember? We did this exact same thing with s's. Except for instead of j omega to the n, this would be s to the n, right? All right. So we do this. Same happens on the right-hand side. And we can then solve for this ratio of y over u. Okay? Y over u, which is the Fourier transform of y divided by the Fourier transform of u. We're going to call it h. Okay?
It's just out over in, right?
It's out over in. Yet again, we're doing the same. I mean, it's very analogous to what we've done several times. It's not exactly what we've done, but it's very analogous to it. And we get this ratio over here of j omegas raised to different powers and multiplying by the different coefficients, right? And this ratio we are going to call the frequency response function, which is something we've already talked about, right? We've just learned how to derive it in another way. But it's exactly the same way, right? We found the frequency response function before by finding the transfer function first, right? And then we plugged in s equals j omega. Remember that? What we've done here is just plug in s equals j omega before we got to the end. But it's the same process as finding the transfer function. So this frequency response function, you could find the transfer function and plug in s equals j omega, or you could start off with the Fourier transform and think of it in terms of frequency response function from the beginning. So those are the two options that you have, but it's 6 or half a dozen, and just you get to the same result for the frequency response function. So we're just sort of like closing the loop here, okay? So like we've talked about the transfer function, we talked about the frequency response function from the transfer function, and now we're finding the frequency response function directly using the Fourier transform. But they're all equivalent ways of doing things. So the following block diagrams are useful. So now that we've done all of these different things, let's think about the frequency response function a little bit. So the frequency response function, you put in, so this is the Fourier transform of the input, right? U of j omega. You put it into the frequency response function, and you get out y of j omega, which is the Fourier transform of the output. The transfer function takes u of s, which is in fact the Laplace transform of the input. However, the Laplace transform, we have written it in terms of the s variable, previously the input, and that was just in complex form. It turns out that it's equivalent to the Laplace transform of the input as well. So if you want to think in terms of Laplace, then you have an input, a transfer function, and then an output, which is in the Laplace domain as well. So that is fine. You could also think in terms of the system transfer operator, H. I remember way back when we talked about operators. U of t would go in, and then y of t would come out. That's thinking completely in the time domain. So these two are thinking more in the frequency domain, so the frequency response function and the transfer function are frequency domain representations. The system transfer operator is the time domain representation, but they're all telling you the same thing, how the input evolves to become the output. So if you give it an input, how does it change that input into the output? And that's what all of these representations do. And we've learned like so many different ways of explaining of how to describe a system. It's almost like, you could lose the thread of it because we've just done so many different representations. So I just want to make sure that it's clear, though, that all of these are ways of describing how an input relates to an output. And they're all used in different situations for different types of analysis, okay? And we've learned how to do several different types of analysis with them. And the Bode plot has been one of the central ideas in the frequency domain, right? We've been able to look at the Bode plot and see how each frequency of the input becomes a frequency in the output, right? And so there's this idea of filtering or shaping the input spectrum into the output spectrum. And we've been learning about that, and you guys did really well on your midterm on that stuff, so I feel confident you guys are understanding this. So we can solve the single input, single output ODE, so the one at the top of the page, this guy. We can solve it for y of j omega. So we can solve it by solving star, which is the transfer function, or the frequency response function equation here. Solving it for y of j omega and taking the inverse Fourier transform. This is something that we haven't done yet. So if we wanted to solve for the output, we could solve for y of j omega, right, by just multiplying both sides of this equality by u, right, by u of j omega, and then taking the inverse Fourier transform of both sides. The inverse Fourier transform of the Fourier transform is just the time domain function y of t.
Inverse of the Fourier transform, you said?
Yeah, so actually that's what this says here. So this formula says y of t, which is the time domain, is equal to the inverse Fourier transform of y of j omega just means the Fourier transform of y. So we could write over here if we wanted to, just to remind ourselves, y of j omega is by definition the Fourier transform of y of t. Okay, so what this says is that y of t equals the inverse Fourier transform of the Fourier transform of y of t. So if you take the inverse of the Fourier transform, you're just undoing it, and you get y of t out. That's what that says. But y of j omega from the start equation is just equal to, so this, let this be h, so this is h. It's just going to be h times u, right? So y is equal to h times u in the Fourier domain. So we just plug in y of j omega equals h times u. And if we do that, we have an expression that is the Fourier transform of y. So we need to take the inverse Fourier transform, which we do here, and we would get out the time domain function. If you have y of t, you have solved this differential equation, right? You found y of t. This is what you guys did with Laplace as well, right? This is what you did with Laplace. You took the Laplace transform of both sides, and then you solved for the Laplace transform of your output, y. And then you take the inverse Laplace transform to find your time domain, y. Okay, so it's the same thing that we're doing here with Fourier. You can do the same thing with Fourier and Laplace. It's useful. We don't spend a lot of time on solving differential equations with this, but it is a very powerful tool, and so you need to know that you can do it. And you can use the table to help you do inverse Fourier transform. That's always the hardest part. Fourier transforms are typically the easy part. The inverse ones are usually the hard part, okay? And we could spend 3 weeks doing inverse Fourier transforms. Like, there's a lot to it. But one thing that's helpful is some of these packages out there, like Mathematica and Wolfram Alpha and whatever, but Mathematica is the more powerful version. It's in those computers downstairs. You guys can take the inverse Fourier transform of something with that, which is nice. It is actually, I've run into a few that it doesn't know how to do, and so you have to do them manually. So it doesn't always know how to do it, but for simple stuff it can do it. Okay. And we are, so now that we've seen, I guess, we've seen what the Fourier transform can do for us. It gives us another way to think about the frequency response function, right? It also gives us a way to solve a differential equation if we so desired. And remember, last time we learned that the Fourier transform allows us to write a frequency domain representation of an aperiodic function, right? So transient is one way that people call an aperiodic function, a function that is not repeating itself. So we learned how to write a Fourier series for periodic functions, and we're now learning, we learned last time how to write one for aperiodic functions, and now we're able to describe any of these inputs that we have as a Fourier transform. So the input doesn't have to be periodic for the Fourier transform to apply. It actually applies in any case. Okay, so now here's the part that is really just review. We usually consider the magnitude of h of, we usually say j omega. It is a function of omega, actually, but of h of j omega and phi of j omega, which are defined as, the magnitude is the square root of the sum of the squares of the real and imaginary parts, right? And the phase is the arctangent of the imaginary over the real, which is something we've talked about quite a bit in previous weeks. And this is the complex plane representation, just like we've talked about a lot. So recall that we're only considering sinusoidal inputs. We can, in this discussion, consider this, but although I would like to say that, to clarify once again, to repeat that this is not, the Fourier transform applies to any function and not just to sinusoidal inputs. When you have a sinusoidal input, though, remember that we have an output that is a scaling of the input. It's a sinusoid at a frequency that is the same as the input frequency, and you have a new phase. It's a very important result. We've already seen this result. So it means that the steady state response of a function to a sinusoidal input is sinusoidal and has a new amplitude and phase depending on the frequency response function. For this reason, the frequency response function's magnitude and phase give us significant insight into a system's steady state response, and we like to plot them. So here's a review of the Bode plots. I'm just going to sort of skim over this for you guys because we've done this in detail. But remember that we're talking about the magnitude and the phase of h of j omega. It's logarithmic in decibel representation, and we could do an example, which we've already done, right? We've already done this example, and so you already have this in your notes. So I just wanted to reiterate that we can plot this h of j omega just fine, but I wanted to start off by at least doing it deriving the frequency response function from the Fourier transform instead of in the way that we did it before. So that's the only part of this that we're actually going to go through, is finding the Fourier, finding the frequency response function of this input-output differential equation using the Fourier transform, which is something we haven't seen. We've seen all the rest of it before. So I want you guys to help me to find the frequency response function using the Fourier transform. I want you guys to tell me the first step. What's the first step? How do we find it from this differential equation? How would we have found it before? On your midterm exam before spring break, I know, eons ago. How would we have found it back then? How would we have found the frequency response function? Do you remember? Yeah, we would
Transfer operator first.
Yeah, so you could either do the system transfer operator method, or you could do the transfer function method that we learned was to transform this into the S domain. So ta S times y, capital Y of S, the complex amplitude, plus y of S equals k u of S, right? That would have been, and we would solve for y over u. That's how we would have done it, and then we would have plugged in S equals j omega. But let's just go through and use the Fourier transform way, which is very, very similar. But, you know, we just learned Fourier transform, so we're trying to get exercise with this. So what is the method we use? Just, you know, right up here. Right there, this nice, colorful demonstration. We started off by taking the Fourier transform of each side, right? So let's do that. How do we take the Fourier transform of the left-hand side of this equation? It was something like Fourier transform of ta y dot plus y equals, you gotta take the Fourier transform of the other side too, right? So, what did I say earlier? If you have a sum of two time domain functions and you want to take the Fourier transform of that,
Can you use as a linear operator and apply it to each term?
exactly, is it a linear operator? I like the terminology and everything here. So Fourier transform of ta y dot plus the Fourier transform of y equals, you can pull the, well, so on this one, can we do something on this one too? Pull out the k, right? So we could pull out the k, so it's k times the Fourier transform of u. Left-hand side here, we could pull the ta out, right? That's a constant, so ta times the Fourier transform of y dot plus Fourier transform of y, we typically write as what? Big Y of j omega. Yeah, I know. Thank you. Gotta keep me on my toes. And then k, now decide times, what would we write fu as?
Capital U.
Capital U of j omega. And so we're getting close. We just need to take the Fourier transform of the time derivative of y, which we can do, we know it's just something times the Fourier transform of y, right? So it's ta times what? Is not the quadratic formula. I promise.
Try it.
Something else. So the Fourier transform of a time derivative, remember we had that property from the table we used last time, that if you want to take the Fourier transform of time derivative of y, that's just equal to something times the Fourier transform of y. J omega, yeah, good job. J omega times y of j omega plus, we still have this other y of j omega here, equals k u of j omega. So now we've got a y of j omega in both terms. We could factor that out. We're solving for y over u, right? So this implies, so I'm going to, h of j omega is what we call the frequency response function, right? And that is always defined as being y of j omega divided by u of j omega, which would be what? If we factored out y here, divided everything else over, and divided both sides by u.
K over tau second.
Yeah, ta j omega plus 1. That's our frequency response function. There we go. It's not so bad, just, you know, go through the steps. We can do the magnitude and phase, but we've done this so many times now that I don't even want to do it anymore, because you guys, it's like getting old hat at this point. And I think you guys would be bored if I did it again. We actually did this example, so I don't want to do this again. I just really wanted, I wanted to give some motivation for finding the frequency response function, and that's why I wrote this problem like this, but the rest of it's old hat. So we want to be new hat and move on to the project discussion. That's what we want to do. Okay, so let's conclude this lecture with that. And just suffice it to say that we could find the magnitude and phase and use Bodaplots. And whoa, my font didn't come through here. But this is, of course, the magnitude plot, and this is the phase plot. And they're familiar to us. We could draw them. We could sketch them ourselves at this point. We're feeling mighty confident in our abilities to sketch them, right? Okay.